All right, so hello everyone. I'm James Crowley. What I'm going to present here is actually partly inspired from the results of the AI for You working group on collaborative AI. I have a number of topics I'd like to cover first. In order to set the foundation, I want to go back and visit some of the questions that we've heard this afternoon. For example, what do we mean by intelligence? I'd like to give you a workable, usable definition, at least for when we discuss collaborative AI. Say a few words about perception, action, cognition, and categories of intelligent services. This is sort of a wink to Michelle and Wendy, who were there, because we've talked about this subject for over 20 years. And a little bit of background from deep learning, because there's been a breakthrough in the last 3 or 4 years that's changing the game. And I'll say a few words about that: transformers and self-attention. Most of what I'll talk about will be the hierarchical framework for collaborative AI that we developed in AI for You, and I'll finish with some research challenges and conclusions. But let me start by what do we mean by intelligence? Now, I know that there's a lot of discussion that what do we mean by intelligence? We can't really define it. But let me say that for our purposes, Turing gave us exactly the definition we need. It's an empirical definition. Turing set up his famous Turing test, where a human interacts across a terminal, a teletype, with another agent, which may be a human or an artificial agent. And the interaction is supposed to reveal to the human whether or not the other agent is human or artificial. And if the human cannot reliably judge whether he's interacting with a real person or an artificial system, then you could say the artificial system can be intelligent. Well, that's an empirical definition. It doesn't say anything about how to make the intelligence. It just says what it is. And we can generalize that now using modern technologies to human level performance at tasks requiring perception, action, communication, or interaction. And let me say that I'm aware that there is a community of people who debate this, and in particular, a very good paper by a University of Pennsylvania professor named Wang, who goes beyond, who builds on Turing's definition with some really interesting insights about limiting information and limiting computing time. But let me say that for today, for what I'm discussing here, Turing's definition is quite adequate. Human level performance at tasks requiring perception, action, communication, or interaction. So in fact, what I'm going to do across this talk is build a glossary. So here's the first item: intelligence, human level performance at tasks requiring perception, action, communication, or interaction. I also want to talk a little bit about perception, action, cognition, and emotion, and in particular, multimodal perception. Well, what do I mean here? Perception is awareness of elements of the environment through sensation. That's a classic workable definition. Lots of people in cognitive science use it. And action is movement to affect or sense the environment, okay? And something I say to my students that's rooted in neuroscience, and there's neuroscience foundations for this, that perception is active and action is perceptive. There's not a clear boundary between the two. You sense by acting and you act by sensing. Human action and perception use multiple modalities. We are fundamentally multimodal. What is a modality? Why, it's a channel for perception or action, including communication. It's a form of action. Okay. Perception, of course, vision, audition, olfaction, the classic 5 senses. But beyond that, other means of perceiving, which use intelligence and artifacts. And of course, action as well: manipulation, locomotion, communication, etc. And I'll note that actions can be semiotic for communicating, they can be systemic for perceiving, and they can be ergodic for changing the environment. Okay, so with that out of the way, let me point out that what I'm interested here is in particular multimodal interaction, which is a form of tightly coupled perception and action. The actions of one agent are immediately perceived by a second agent and used to generate actions, reactions if you like, which are then perceived by the first agent. So when I talk about interaction, I'm talking about some form of tightly coupled perception action between 2 or more agents. Tightly coupled perception action involving 2 or more agents. We're building our glossary. Now, the work that I'm basing that on actually goes on to discuss quite a bit cognition and emotion, which is not so relevant to this talk. I just wanted to mention that I have definitions for them. But I also wanted to mention that they're actually quite consistent with what Kahneman said. We heard earlier today about Kahneman's System 1 and System 2. System 1 is intuitive, based on experience, enables fast, rapid reactions, but can be wrong. And system 2, which is slow and deliberate, based on cognition, enables planning and explanation, but is sometimes too slow to save you, especially if you're about to be eaten by a tiger or some other kind of ferocious cat. Some of the things we discovered in our experiments a few years ago is that emotion and cognition guide action and perception, and even you can demonstrate experimentally in the lab that emotion guides cognition. That was the results from an ANR project and the subject of a paper by my doctoral student, Thomas Kuntz. But as I said, that's not really the topic to be discussed here. I could spend 45 minutes on that topic, but not today. I also wanted to make a real quick wink to something that Michelle and Wendy and Joelle and I have been discussing for at least 20 years, and probably even more than that. I remember one very interesting evening in Cyprus about 20 years ago where we chatted about this. And I know Michelle has been publishing about it, but so have we. Categories of intelligence services can be defined by the nature of the interaction. And in particular, we like to define a set of categories: tools, effectors, media, and advisors. And what I'm going to do today is introduce a new category called collaborators. Now, as I said, I saw a paper, I think it was 2009 from Michelle that talked about this. We have it in our 2015 paper. But actually the idea of categories of services goes back even much further than that in human-computer interaction. When people reacted that most computer programs, most intelligence services were essentially tools, but you could also build services to inspire affection, to give humans new perception, and to advise humans. So what I want to talk about today is a new class, which I'll call collaborators. Intelligent systems that act or interact with people to achieve a common goal, that share awareness of situations, plans, abilities, and practice. That's what I want to talk about today. So let me define collaboration as a process where two or more actors, agents, things that can act, work together to achieve a shared goal. So collaborative intelligent systems are intelligent systems that work with humans as partners to achieve a shared goal, ideally understanding a mutual understanding of the abilities and the roles of each other, but in office, often it's mediated by simpler things such as protocols and social customs. So let me add collaboration to my glossary, a form of interaction where two or more agents act together to achieve a shared goal. Now, these are hard problems, but fortunately, we've had a breakthrough in the last few years coming from machine learning. And as someone pointed out, as I think it was Theo in the previous talk, this is actually technology that's been around since the 60s. Okay? Deep learning, which is essentially trainable universal function approximators. And I thank Theo for giving the slides about discriminate systems, because actually those were similar to some slides I removed from my talk to keep in my 45 minutes. But let me say just a few words about artificial neural networks. The two key innovations about building on perceptrons happened in the mid 70s. One was to replace the hard decision surface of a perceptron with a soft decision surface, making the functions differentiable and allowing them to be learned by backpropagation, which is a distributed form of gradient descent. These are now very well-known techniques, worked out in the 1970s as a method to provide an alternative to symbolic computing. And of course, with sufficient computing power, you can make deep layers of these things. And what you end up with is a neural network as a trainable universal function approximator, like Turing's universal function. Only Turing, he's speculated that with a Turing machine, we had a universal function, but no one knew how to program it. The real world is just much too complex. But with sufficient data and sufficient computing, and I'm talking planetary scale data and massive amounts of computing, we can make arbitrarily complex universal functions using neural networks, using Hebbian propagation. It's a whole different style of programming that we all learned in computer science. We're essentially propagating energy. Now, the important messages here is that while deep learning was originally developed for recognition, assigning category labels to signals, the same technology can be used for generation, generating signals from category labels. And this can be used to learn to generate natural sounding speech, natural language, synthetic images, animations, robot movements, and realistic talking heads. And indeed, if you're not aware, be aware that we can use generators and this technology to generate very realistic deep fake. You can go online and do it today. There's services on the internet that do it. Now, in particular, if you put the discriminator together with a generator, you get something called the autoencoder. And essentially, the key concept is here, you don't need training data. Well, the data is its own training data. You don't need labels. This is not supervised learning where you have to generate a label in order to train on data. In this case, the data is its own ground truth. The training data is the target. And the difference between the reconstruction and the original data is the error signal. And what this does is compress the data to a minimum independent vector. Now, back in the 70s, Jeff Hinton and others, and those of us working on neural networks back then, used autoencoders to compute a form of principal components analysis. We didn't have ground truth data with our data. We just had lots of data. And we developed my colleagues developed backpropagation using autoencoders as essentially a way of avoiding the fact it didn't have ground truth. Around 2002, 2003, Andrew Ng proposed that we could add a theoretical sparsity term, not just using error for reconstruction, but also sparsity, and get to a form of independent components analysis, essentially using this to learn categories that describe data. And very quickly, we discovered we could learn a sparse code for data, for very noisy data, by reconstructing it. Now, this turns out to be extremely powerful because you can use this technology for one thing to generate very realistic output. Well, here's an example using a variational autoencoder where we trained the system to reconstruct a dancer, and then you can slightly tweak or do transfer learning on the input side and get it to recognize one dancer and animate another. The same thing can be done with talking heads, so that I can have my own face animating, for example, Donald Trump, and having Donald Trump say all kinds of outrageous things. There's a movie of Barack Obama doing that, of Donald Trump, made with deep fake, made with a variational autoencoder. It's very interesting. It's been around for about 5-6 years. But there's more than that. What you can really do with this is self-supervised learning. This opens up the entire internet as training data. All of recorded human knowledge can now be used as training data just by using autoencoders. The way this works is we replace missing parts of the data, that's called missing token replacement, and we use it to predict adjacent data, next token prediction. Self-supervised learning unlocks all of recorded human knowledge to machine learning, provided we have enough computing and access to world planetary scale data, which is exactly what's happening now. So let me mention self-supervised learning, learning by reconstruction and prediction. Now, around 2017, there was a breakthrough, a revolutionary paper by a guy at Google, Viswani, actually by about 15 people at Google, showed that deep convolutional and recurrent networks, which required label training data, could be completely replaced with stacked layers of autoencoders, stacking the encoders on one side and the decoders on the other side. The key paper here is called Attention is All You Need, because the key to making this work was the notion of attention. Self-attention, well, attention in general, selects a subset of the data, in this case, a subset of the latent variables of the encoder to associate with other data. And this has been used to generate, well, transformers, in particular, two very popular ones, BERT and well, I'll get back to that in a second. But it's become the dominant technology for natural language processing, GPT. The other one was GPT-3. It's become the dominant technology for natural language processing and has completely taken over the natural language processing community during the last 5 years and opened up amazing new abilities, learning just essentially by training on Wikipedia or the World Wide Web. And what we now have are technologies that can generate very realistic text, realistic stories. You give them the first sentence of a story and they'll go on in fabulating a whole complete story. One of the interesting properties of this is that it's extremely easy to do multimodal perception and multimodal generation. You simply concatenate modes. You take those latent variables by the encoders, put them side by side, and use attention to associate them, and then train by reconstruction and prediction. Okay? Used with multiple modalities, self-attention determines the relevant information in each modality. It solves a lot of those hard problems that for years those of us working in multimodal interaction have been struggling with, about how to combine modalities and how to fuse and fission modalities at different levels of abstraction. Self-attention can be used, of course, to associate words with perceptions, and thus you can recall a perception using a word, or you can recall a word from the perception, which is really interesting as well. They've been used for all sorts of modalities. They're currently creating a revolution in computer vision. Since last year, all of the major computer vision conferences have been dominated by transformer papers. They've been used in speech recognition, where they're completely revolutionizing also the ability to recognize and to generate spoken language. And they're invading robotics right now, where we can generate very realistic articulatory motions for arms and walking and things like that. Okay. One of the more interesting developments that I've seen in the last year has been what's called the episodic transformer, which doesn't only process the immediate input signal, but also processes whatever came over the last short-term period. It's a kind of short-term memory for transformers, combining the recent past with the inputs from the different modalities. In this case, it was used by one of our doctoral students at Grenoble to generate robot actions for manipulating objects, but it can be used for a lot more than just that. And it can be combined with deep reinforcement learning. We heard about that earlier this afternoon. Reinforcement learning has been one of those things that machine learning people have struggled with, again, since the 1970s. Essentially, you're trying to learn a policy for how to act under different situations based on the state of the environment. I'll have a lot to say about that in a minute, but it can easily be combined with transformers to have deep reinforcement learning with transformers, learning to do things like, well, affect emotion, how to recognize and generate emotions in people. I'm showing a parallel robot here, but one of my doctoral students is working on exactly that right now. Okay, so those are the preliminaries. I said that would take 15 to 20 minutes, and apparently it's taken 18, so we're right on schedule. What I want to spend now is another 20 to 25 minutes, well, 20, on the hierarchical framework for collaborative AI that was developed in AI for EU, because given transformers and given what we know about perception, action, and multimodal perception, and given what we're trying to do with intelligence, well, we now have the enabling technologies we need to really start working on practical collaborative intelligence systems. And for that, what we did in that working group was develop a hierarchy, at the core of which is reactive, above which we have situational, operational, practical, and creative interaction and collaboration. Reactive is tightly coupled perception action, multimodal, of course. Situation aware is where perception and action are mediated by shared awareness of situation. In operational, they're mediated by shared authority over tasks and activities, typically with protocols and customs. In practical, it's about sharing the knowledge of how to act, teaching each other, as we just saw, about what's the appropriate action to take in each situation. And of course, creative is a new area that, well, we don't have very much there yet, but there's interesting opportunities being opened up in creative collaboration. I'll finish with that. Well, let me start with reactive. Well, tightly coupled perception where the actions of one agent are immediately sensed and interpreted as actions by the other. Well, a trivial example is the modern automotive systems for lane following. You can buy this in your car now, typically using some hardwired perception algorithms and something like a PID, feedback controller. We can also do it with end-to-end systems, learning with deep reinforcement learning and transformers. But that technology is, well, it's in the lab, but it's not getting very far so far, but it's coming. Well, what you find in a car are things that, for example, lane assist, which will generate auditory alarms and control forces on your steering wheel if the car starts to go out of the lane, or blind spot detection, which will beep if there's somebody in the blind spot, or brake assistance, which will modulate your brakes based on how far away the obstacles are. That's all fine, but it's hardwired, hardcrafted, and not very interesting. More interesting is the idea of reactive social interaction, where we have tightly coupled perception action for social interaction, where the actions, the communications of one agent are immediately sensed and interpreted by the other. For example, recognizing emotions from facial expressions and posture from an agent, learning to recognize and evoke emotions. That kind of emotional affectors that my graduate student is working on are examples of reactive social interaction. Another example done with transformers is communicating agents, things like Replica. Replica is a system, you can look it up on Google and play with it. It's online and available. It's based on GPT-3, OpenAI's GPT-3 that was essentially trained on Wikipedia, coupled with a really realistic synthetic face and body and movements and gestures and excellent emotional expression. Replica learned a realistic imitation in the language patterns of a young female from emails and text chat. The reactions are socially appropriate, but the interaction lacks context. If you play with this thing for more than 5 or 10 minutes, you realize that she's just playing with you. She doesn't understand really what the conversation is about, and there's no understanding of situation. So while these things are really interesting reactive social interaction, they're not really situationally aware. To go further, what we need to build is understanding of situation. I want to say a few words about that. That's the layer here I'm going to spend the most about because it's the one where we have the most scientific foundation already. Okay, so an example, okay. Have you seen my glasses, Bobby, the robot? Yes, they're on the desk in your office. Would you like me to get them? So the two agents here share a notion of what are the glasses, where is the office, what is the desk, and the facts the glasses are on the desk. This is an example of situation-aware interaction. Perception, action, and interaction mediated by shared awareness of situation. But what is that? Well, situated interaction, of course, has been studied for a long time in sociology. Lucy Sussman, with her career, is the study of interaction between an agent and its environment. And the core concept is, of course, mediation. Situated interaction requires awareness. And awareness is a core topic studied in human factors and other areas of cognitive science and ergonomics. Awareness, commonly defined as vigilance against danger or difficulty, having knowledge of things, the ability to perceive, feel events. This has really been studied in human factors since the early 20th century, when it became a key problem in aviation, particularly in aviation during World War I. And one of the key people here that I like to read from is Nika Ensley. She wrote a book, Situation Awareness, Analysis, and Measurement. She's also done a whole series of studies about situation awareness when piloting aircraft, in particular with instrument flying. Situation awareness, according to Ensley, is the perception of relevant elements of an environment in the volume of space and time, comprehension of meaning, and projection of their status in the near future. So it's not just recognizing categories. It's detecting, assimilating, and projecting. And I had a few slides about processes for situation awareness, but in the interest of time, we'll skip over those now and go directly to what do we mean by situation. Well, situation models are actually a core concept in cognitive psychology. And there's several communities that build on the work of Philip Johnson Laird from University College London. Situation models widely used to provide context for story understanding, to interpret ambiguous or misleading perceptions, to reason with default information, and to focus attention. Well, that's interesting, focusing attention. We're getting back to our transformers. And in fact, what I'm going to show in just a second is this actually converges quite nicely with the transformers. We'll talk about that in a minute. Situation models provide a software framework for building intelligent systems. And I say that because my own group has built quite a few of these systems, where at the core of the behavior of the system was a situation model. The idea is one of a state space. Situations are composed of relations between entities. An entity is any relevant observable phenomena. Anything you can perceive is an entity. Entities have properties that allow us to compute associations, which are called relations that formalize with predicates. And then the situation is simply a set of relations between entities. It's a state. And we can attach behaviors to states, which are condition-action pairs, and make a whole network of states, of possible states with state transitions, which is called the situation model. And this is what cognitive scientists have been using for at least 30, 40 years to understand group activities and situated interaction. So let me add that to my glossary. An entity is any observable phenomena. A relation is a predicate function, an association between entities. And a situation is a set of relations between entities, a set of relations that associate entities. So the research challenge here is how can we create technologies that permit humans and intelligence systems to share understanding of the situation? Well, actually, the interesting opportunity here is if you look at those latent variables that I spoke of with transformers, they are a form of situation model. They're a state. And we can associate language with them just by concatenation so that we can put words with that state. We can put explanations. Now, the idea here is how can we get humans to share situation models, particularly if they've been learned with things like transformers. No one's done it yet, but it looks like a low-hanging fruit to me, and I think it's a really interesting challenge. In some circles, this is called finding common ground for collaboration. I'll come back to that. Common ground through explanation or instruction or demonstration or experience through shared situation models. Well, what can we do with it? Well, the interesting thing is operating together, operational collaboration. Well, here's a trivial example. Robbie, please stir the soup and don't let it burn. Okay, I will stir the soup. I will not let it burn. This is shared authority over initiating, conducting, or terminating tasks and activities, basically deciding who does what. And mostly between humans, operational collaboration is mediated with roles and protocols. We do what we do with each other. We cooperate with each other based on protocols that we've all learned for a long time or that we explain to each other. So shared authority over initiating, conducting, or terminating tasks. For example, protocols for meetings, for games, talking on the phone, for giving talks in a conference, or for buying soap in the shop. Okay. Typically, in a meeting, you have roles. You have people playing the role of the speaker, people listening, maybe a moderator directing the speakers. The roles provide liberty to take actions. They say who can do what and who can't. They allow us to expect certain behaviors and expect the interdiction, the forbidding of other behaviors. And they provide guidelines to govern actions and behaviors so that the interaction flows well. Okay? And essentially, anytime you buy bread in a store or anything else, your interaction is mediated by a shared protocol for polite interaction. Okay? There's a whole protocol that simplifies the interaction. The storekeeper doesn't need to figure out why you're in the store, and you don't need to figure out how to get the loaf of bread. You know the transaction, he knows it too, and you just go through it. So adding to my glossary, protocols, rules and guidelines that govern actions and behaviors. So operational social interaction is typically mediated by social customs. Okay, I mentioned meetings, games, etc. But we've got open research challenges. How can we allow systems to learn those social protocols from observation and explanation? Or as we saw in Tio's talk, how can we teach systems about how to behave, about what's appropriate and what's not appropriate? We need, obviously, shared situation understanding, but we also need shared discussion of the sequences of situations that make up an interaction. And that typically requires practical experience. This is the level above operational, which in AI for You we call praxical. Praxical collaboration is the exchange of knowledge about how to attain goals or maximize value based on experience or training. I don't know why I dropped the training there. A lot of practical knowledge is based on training. So, your household robot asks you, which pot should I use to make the spaghetti? Use the small blue pot in the left cupboard. Praxical collaboration, exchange of knowledge about how to attain goals and maximize value. It involves shared strategies of how to navigate a complex situation, such as traffic or sporting events, or how to assemble or repair a device. Classically, this was done with rule-based expert systems. And in fact, 40 years ago, I used to teach how to do this with rule-based expert systems. But those are very brittle technologies that are really expensive to build. Research challenges right now are how to permit humans and intelligent systems to collaboratively plan, how to decide, and how to exchange knowledge about what works and what doesn't work for a domain. So praxis, knowledge of how to do things based on experience or training. Above that, we have a wilderness, if you like. We have a big challenge for creative, because in theory, at least, collaborative systems could greatly enhance our creative abilities. And in fact, they do, because they're artificial systems and informatic systems and machine learning-based systems tend to be quite complementary to humans. Each of us do good things, and together we usually can work better. Of course, the trivial case in the house of what should we make for dinner tonight, 2 or more partners work together to solve a problem or create an original artifact. This is actually something that's been in informatics for a long time. Back in the late 70s, early 80s, we had expert systems that, in a sense, were collaborative expert systems, were collaborative creative systems. They helped a user develop an artifact or a course of action. E-myocin was a rule-based system for antibiotic therapy. R1 helped an engineer design or configure VAX computers. IBM went at this problem with Watson and cognitive computing. I think they've pretty much concluded that they've been made obsolete by transformers. But for a long time, that was their big goal. More recently, OpenAI has released something called Codex, which generates computer code based on a description. You say, I would like to have an HTML, or no, I would like to have a C language program or whatever computer language you like program that does X, Y, and Z. And GPT will produce it for you. You may have to tweak it a little bit, but it's a lot easier to tweak it and debug it than it is to start from scratch. And this is being built into programming tools now. There's a big scandal right now about use of AI at Apple, and it turned around Apple's use of AI from doing automated layout of integrated circuits. I'm not quite sure why the scandal erupted, but all of the people building AI circuits, and in particular Apple, are using these kinds of generative systems and transformers to do layout designs, which are much more efficient than anything a human can do. So technologies that permit humans and intelligent systems to collaborate, to collaboratively plan and execute operations, including contingencies, solving your problem in the power grid management problem, for example, where the artificial system, the intelligence system, can see results and things that the humans can't see, and vice versa. And of course, technologies that permit humans and intelligent systems to collaboratively design artifacts. So how do we get there? Well, this opens up a whole range of research challenges. And in Humane AI Net, we've centered on the theme, or almost the slogan, of finding common ground is the way to go after this. So I want to say a few words about finding common ground and the importance of narratives, and then talk a little bit about challenge-based research. And this is where I can modulate the length of my talk, because I could talk for 10, 15 minutes about different forms of challenge-based research, but we'll arrange it so that we finish at 45 minutes, so we have some time for conclusion. There was a paper last year in Nature by a list of authors, very prestigious list, called Cooperative AI, Machines Must Learn to Find Common Ground. And they define common ground essentially as abilities to understand and communicate knowledge about situations, operations, interaction, and practice. Okay. And required, of course, is shared understanding of situation, shared understanding of operations, and shared practical knowledge. And they raised a challenge of how can we get cooperative systems, cooperative AI, intelligence systems to do these kinds of things. One of the key ways of doing that is with explanation. So a classic definition of explanation. So I'm actually kind of irritated right now with all the explainable AI people, showing me the activation region of an image when it's recognizing a tumor in a lung. Okay, that as a machine learning person, I know how to understand that activation energy as the area where there might be a tumor, but that's not an explanation. An explanation is a statement or a narrative that makes something clear or justifies an action. When somebody explains something to me in language, they're telling me why they did it or what needs to be done. Generating and interpreting explanations between humans and machines is a key enabling technology for all levels of collaboration. For situated collaboration, the something is the situation. For operational collaboration, it can provide a description of the sequence of intended actions and an intended outcome. For practical collaboration, it can exchange knowledge about how to get things done or what protocols to follow to decide who does what. And for creative collaboration, it can be exchanged for hypotheses or possible solutions. So I'll add that to my glossary. Explanations, a statement or a narrative that makes something clear or justifies an action. Well, narratives. Maybe you've read Calvin and Hobbes. Dad explains science. Why does the sun set? It's because it's hot. Hot air rises. The sun is hot in the middle of the day, so it rises high in the sky. In the evening, the sun cools down, so it sets. But why does it go east from west? Solar winds. Okay, these are explanations. Okay, they actually sound kind of credible, but anybody who knows anything knows that they're absurd. The narratives are temporally ordered sequences of situations, usually with causal relations and branches. And an example is a scientific theory. Take whatever scientific theory you can that explains and predicts observable phenomena, and it's a form of narrative. Narratives enable humans to provide descriptions of situations that are not observable, including hypothetical situations, abstract situations, or things that happened in the past. And they allow us to make predictions for things that may occur in the future. They're basically essential for survival. So in a sense, you can formulate a narrative as a path through a situation graph. You formulate it in a situation space, and it's that sequence of situations that make it through the path to which you can attach actions that you can perform or that someone else might be able to perform. Okay. It also allows you to infer things by entailment, because those situations may have entities and relations which are not directly observable, but knowing that you're in the situation tells you that you should expect that entity to be there or the relation to be true. So narratives allow you to infer things about things you've never seen or that haven't happened yet. The role of language. Well, natural language, of course, is fundamental to collaboration. People use language to communicate. We are a collaborative social species thanks to language. Classic technologies for situation models are easily translated to language because they're just predicates, which are verbs, and entities, which are nouns. So you can make a sentence for every predicate and its relation and its predicates. Interestingly, the latent variables from transformers can also be used to generate linguistic descriptions. In fact, the technology was originally invented for just that. BERT and GPT are natural language processing technologies. The interesting research right now is generalizing that technology to go to images, sound, and image sequences, and tactile forces, and everything else we can sense or act. So the research challenge is to demonstrate machine abilities to construct, communicate, and interpret explanations about situations, operations, practical knowledge, and creative solutions. And I suggest that narratives are a key enabling technology to do this. Well, I wanted to make a statement about how research is done these days, especially in the areas of computer vision, natural language processing, robotics, speech recognition, speech synthesis. It's mostly done with offline research challenges. People publish massive data sets and performance metrics and challenge people to do things with them. And this is rapidly developing the enabling technologies that we need, but it's not really getting us to a true collaborative technology. Okay? Some of my favorite examples were visual question and answering. There's quite a few data sets and a regular annual competition about this that you can see in workshops associated with conferences. And every year the performance gets a little bit better. Okay? Generate natural language answers to a question about a video, okay? And essentially learning question answer pairs. There's challenges about audio narrated and textual narrated clips of how to do things. There's lots of data and lots of research challenges for that. The Epic Kitchens one is one that my students have been competing in for the last few years. This is hundreds of hours, 20 million frames of people doing things in their kitchen, cooking. And there's all kinds of interesting challenges about recognizing the actions, detecting actions, anticipating actions, cross-modal retrieval. But the big daddy right now is egocentric 4D perception. This is a new data set that's come out with a whole range, a whole cluster of challenges that's been done. It's a huge data set in the wild, captured by 926 camera wearers from 75 worldwide locations, with all kinds of very rich multimodal data, language, speech, 3D, 2D, and a set of challenges around them, one of which is challenges related to episodic memory. How can we build episodic memories from these huge data? Things about diarization and social interaction, things about forecasting, what's going to happen next, short-term and long-term, okay? And that's essentially the way that the research is being advanced piecemeal right now. The interesting problems is how to go beyond that. How to go beyond that to actually build systems. And I think to do that, we've got to tease out the problems and separate them into problems related to situated interaction, problems about operational interaction and collaboration, about exchanging knowledge, practice, and about creative. And I think self-supervised learning with transformers is really the enabling technology that's going to allow us to make progress. So the next big challenge is to be able to train systems through interaction. And interestingly, Tio was talking about that subject. So I was kind of disappointed he didn't talk about transformers, because that's where the action is right now. Using things like explanation, narratives, and deep reinforcement learning. Okay, so I think I held to 43 minutes, Wendy, so we have some time for questions. I hope the questions will work, and I hope you all found that interesting. Oh, by the way, the report that was produced by AI for You is available online. The link is here. If you send me an email, I'll send you a pointer to that link and you can download it. It's currently submitted to IEEE Pervasive, and we're waiting for the reviewer comments. Okay, so thank you all very much, and I'll be happy to have discussion and take questions.